Sequence versus series. We talked about sequence conversion. Conversion.
Oh, we're done.
Last chapter, we did not talk about series conversion.
Okay, so 2 and 3.
It's going to infinity. It's not going to diagonal.
Well, the series converges to 0, but the sequence will always have to do.
No, the sequence converges to 0. The series.
The series.
We have a teacher for a reason.
Wait, so
The
sequence is
sequence
infinity.
will be.
But the series is...
The series will converge. Yeah.
You guys are writing, right? My non-multitaskers are being quiet so you can focus. My multitaskers, you might be talking.
Yeah, I'm good.
I said apparently. You can't apparently because I said multitasking.
You only have 2 more.
Oh yeah, because focus on something. Yeah. I mean, we're not a squirrel.
I've never seen each one of them.
Yeah, but did you? Wait, enemy? I mean, you're vegan? No. That's pescatarian. Fish cats. Yes. They're the meat of the sea. They're like the cow meat of the sea. But without they would make like a good amount of our water goes towards Actually, I don't like steak. Steak is so
Delicious.
it's like dry. I don't like dry. It's just like, I don't. What do you mean, Cal? What'd you have?
Alright, kiddos. What does it take for a sequence to converge? What does it take for a sequence to converge?
The series.
Nope.
It approaches as it increases.
Never use it in calculus.
As
What approaches?
the function.
Function is increasing.
The function.
The function of
Dos sequence.
a sub n
A sub n.
or the nth term. So if the nth term converges as n, or the kth term converges as k, approaches infinity, then yes.
Yeah.
The sequence converges if its terms converge, right? The sequence converges if the terms converge. So when, in chapter 9, our chapter 9, in the old chapter 9, whatever, a sequence would converge if the limit as n goes to infinity of a sub n equaled a constant. True? And a sequence would diverge if the limit as n goes to infinity of its terms diverged or approached infinity or negative infinity or oscillated between, ooh, did you catch it on the test yesterday?
Wait, what?
If it bounces back and forth and back and forth and back and forth and doesn't stabilize. It's okay to say with number or a problem.
Oh.
Maybe one did and one didn't. Anyway.
Yeah, one of them did stabilize. It went to 0. Someone hasn't taken
Okay,
the test.
shush. Just everybody stop, but thank you. You're right. Shush. Okay.
My bad.
Wait, who did
Okay.
take the test?
Let's just focus on what we need to focus on. So a sequence is really easy to figure out convergence if you can take a limit to infinity. As long as there's not like a negative 1. Anyway, so what makes us need to take a whole time out and an entire chapter on series convergence?
You're adding some button.
It's a lot harder. Okay, so come up here. A series converges if its sequence of partial sums converge. What does it take for a sequence to converge?
With
Partial sums converge.
No, sequence is
A sequence, if it,
There are two different words. Eyes on me, off the board. Eyes on me, off the board. There are two different terms, sequence and series. Sequences are separated, the terms are separated by commas. There is a formula, a pattern, usually, to how you progress from one term to the next, but there is no accumulating of the terms. You just continually keep progressing to new terms. A series is the sum of all of the terms of a certain function. A series is separated by additions. The more terms you include in a series, the more the sum expands, or if it's a negative, possibly, the more the sum changes, the more terms that you are adding together. So every infinite sum has an infinite number of terms being added together. So every single one of these up here, the infinity on top says how many terms are being added together? An infinite number. All of them. Okay. For a sequence to converge, commas, separate, not accumulating, for a sequence to converge, the limit of the nth term, its terms need to converge. True? Okay. For a series to converge, the addition continually accumulating, I need the sequence of sums, partial sums to converge. Sequence to converge, terms need to converge. Series need to converge, partial sums need to converge. What do I mean by partial sums? Can we do the infinite addition? No. But can we go, how did you guys explore in your calculator these four up here?
30, 100, 1000.
So you took the first 10 terms, the first 100 terms, the first 1,000 terms. You were taking partial sums. You were partially doing the series. You add the first 10, add the first 100, add the first 1,000. You're like, hey, does this seem to be converging or stabilizing? Good. Difference between sequence, not series. Sequence converging, just take the terms and just look at the terms and just take the limit as n goes to infinity that I just erased of the terms. Series, whole new ballgame. So, as you guys see here, it looks like Pascal's triangle. It's not. That looks like it. The first partial sum would just be the first term. Second partial sum would be the first two terms. Third partial sum, the first three terms. And this makes sense if n starts or k starts at 1. What if I have a series starting at 0? What would change?
A sub 0.
S sub 1 would be A sub 0. Or if you want to, you could say S sub 0, just think that's the initial, right? S sub 0 is A sub 0. S sub 1 is A sub 0 plus A sub 1. Now, it does get kind of confusing. Might be a little easier to make it S sub 1, A sub 0, S sub 2, A sub 0 plus A sub 1, etc. But still, we need to continually keep compounding. We need to continually keep looking at the partial sums to see if they converge. And if these problems on the if these problems were on the AP graphing calculator portion of the exam, I guess we could stop here and just get you guys really good at figuring out whether or not they converge usually. The dilemma is they're not graphing calculator portions of the exam, number one, and number two, maybe what you saw wasn't exactly what's going on. And maybe your conclusions would be false. So, here's the idea. This series, infinite series, will converge if the limit as n goes to infinity of the partial sums converge. That's the big idea on this page 1. So you guys are doing this little exploration. If you need to write anything down, now's the time. You were doing this little exploration. These 4 problems are these 4 problems. You were trying to predict whether or not they converge, whether they converge or diverge. There is no other option. Converge or diverge. If it converges, estimate, ooh, I didn't get this far. Estimate what value the series converges to. Long story short, I think that's too complicated for where we are, because to be honest, even if we can figure out the convergence and divergence of a series, it is very rare that we can actually estimate without technology what the sum will truly be. It is very rare. Sometimes possible, but very rare. For number 1, what do you guys think? Converge or diverge?
Converge.
Oh, you can't even see it? Is this number 1? This is number 1. Go away.
Or 3 halves.
I tried.
No, yeah, you're right.
Okay, so have this one, number 1, I have this one plugged in. Negative 0.5 raised to the k, in case you weren't able to get your calculator to work. Your UN min, if we plugged in 1, it starts at negative 1/2. And then it goes to, what was the next term? Negative 1/2 plus a 4th, minus an 8th, plus a 16th, etc., etc., etc. Every time you could say you're multiplying by a negative 1/2. If you said converge, you were actually right. But soon and very soon, you'll have to have a reason why, and no, your calculator will not be sufficient.
What does it converge to?
1/3.
It converges to a sub 1 over 1 minus r, which would be negative 1/2 over 1 minus a half, which would be 3/2. 1 minus negative a half would be 1 plus a half, 3/2. So 1/2 over 3/2 would end up being 1/3. Negative 1/3.
Oh, I said.
Which is not, I mean, I got to pretty much that conclusion by only plugging in 50. So you got the first partial sum, the second partial sum, the third partial sum, or I should say the 10th partial sum, the 50th partial sum, and I saw negative 0.33333333333. It seemed like the decimals were getting pretty fixed. I did it 2 different ways. Oh, sorry, this was number 2. Close to it. I only did it 1 way. I solved 1 way and I saw the negative 0.33333. So number 1, yes, indeed, it does converge, and the calculator seemed to show us that quite clearly, and it is going to converge to negative 1/3. Number 2, though, when you plugged that one in, did that seem to be getting fixed? I went to the 100th. I could have gone to the 500th, to the 1000th, to the 10,000th. It would have taken some time, because what is your calculator literally doing?
Adding 1 by 1.
Plugging in, plugging in, plugging in, adding, accumulating. It's doing a lot of work, okay? And we don't necessarily have the best processors, we don't necessarily have the best processors over there, but that's okay. Did it seem like this was converging? No. And the truth of the matter is, this is a simple harmonic series, and yes, it will diverge. Yes, it will diverge. Number 3, when you guys plugged into that one, I didn't keep going as far as showing you what the calculator showed, but what did you get in your table for number 3?
Converge to 3.3.
To 3.3?
Yeah. 3.28. That's what I got it.
It does converge, I do agree with you on that. 3.28 though,
That's what it kept adding, and then it kept getting up, so I'm presuming it's what
was it 3.28000000?
No, it's 3.28765. Yeah. And then it got like, the next one was like 3, no, it was like, okay, it was 3.27, blah, 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 and then 3.8, 3.28, blah, 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 blah.
Oh, so you struggle though, that's not going to converge to 3.28, because if it gets that high, it's going to go higher.
Yeah, 3.3.
I tried to go higher, but it broke my calculator.
Yeah, no, literally, right? Just, well, because it's doing so much work. So we're just going to say for right now, converges. To be honest, I actually don't think I could say definitively what that converges to. Yeah. How about number 4?
Yeah, it was converging to 1, but.
What is the series? Isn't it 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1?
Yeah, also matters which.
So hold on, the series, hold on, the partial sums. 1 is just 1. 1 minus 1 is
0.
0. 0 plus 1 is
1.
1. 1 minus 1 is
0.
the partial sums are going between 1 and 0, 1 and 0, 1 and 0, 1 and 0, 1 and 0. Are the partial sums converging?
No.
No. This diverges.
How am I supposed to know?
It's okay, it's an experimentation. Hold on, we have a whole chapter, 6 sections. 5 sections technically, 9.2 to 9.6. Let's keep going. Today, we are covering 2 out of, ultimately, I think 9 convergence and divergence tests.
Ooh, yellow ball.
We're covering 2 out of 9 tests. One of the biggest topics of BC, and our book was going to condense it to 1.5 sections. Anyway, convergence and divergence tests. Ask anybody in Calc 2 what they learned, unless they go to a quarter school, then it might be actually their Calc 3, because they portion it separately or differently. And they will say series convergence, divergence. Some extra things, of course, but series convergence and divergence is the biggest unique topic to Calculus 2. The easiest type of series is a geometric one. Maybe not the easiest. One of the easiest ones is the geometric series test. I'm going to cover the test in order of difficulty to some extent. In order of difficulty to some extent. Meaning, even though I'm going to show the test separately, separate sections, we'll have separate practice, etc., ultimately, what we're trying to get to is the point where you are given some sort of infinite series and you can identify tests to implement to try to figure out what's going on. Narrow down the list of 9 ultimately and say which test should I use for this to be able to tell exactly what it is. It will not be something that most of you can do off the top of your head. It's different than derivatives and integrals in that way. And we do need to have the tests and the ability to reason with them down to be able to solve not only multiple choice but also FRQs. Mostly multiple choice. And mostly multiple choice where they might say, which of the following converge? They might give you 2 or 3 or 4 or 5, and they say 1, 1 and 2, 1 and 2 and 3, 1 and 3 and 4, 1 and 4 and 5, 1 and 5 and 2. Anyway, so you're going to have to be able to do this quickly, because you guys know multiple choice problems should take 1.2 minutes approximately. And if you have 5 different infinite sums to test, whew. So, we're going to work our way up. Geometric series. You guys are used to these because we talked about geometric sequences just a little bit ago. Geometric series. We have a common ratio. Multiply by the same constant over and over and over and over again. True?
Yeah.
The nth partial sum. Ooh, the nth partial sum. We talked about how for a geometric series, the nth term is equal to a sub 1 times r to the n minus 1. We talked about the nth term. We did not talk about the nth partial sum. From pre-calc, pre-calc. From pre-calc, the nth partial sum is equal to, if I can remember it, a sub 1 times one minus r to the n all over 1 minus r. Oh, I think that's it. We don't use it much, sorry. 1 minus r to the n all over 1 minus r. I believe that's right. At least it'll work. The nth partial sum. The nice thing, remember, between geometric and arithmetic is that they both have this constant pattern that is going on. It's not a continuously changing pattern. Arithmetic we'll definitely talk about another day. But geometric and arithmetic have these nice formulas, and some of you guys actually memorized like the nth term formulas for the last test, and that was helpful. Some of you guys, it's more of a logic thing. But the nth partial sum is equal to, so here's the dealio. My question to you is, if this is the nth partial sum, if we're trying to find the infinite sum, what do I need n to approach?
Infinity.
Bigger numbers.
We can do that. Limit as n goes to infinity of s sub n is equal to the limit as n goes to infinity of a sub 1 times 1 minus r to the n all over 1 minus r. In order for this limit to exist, what piece of the formula do I need to zoom in on and analyze?
A sub 1.
Nope. Actually, doesn't matter where we start. R. Yes. Why? Where's the only place that n is even present?
And R.
Okay.
R. So, okay, coming back. I need to analyze the R. When will a constant, because R is a constant, right, common ratio, when will a constant raised to the n as n goes to infinity ever converge?
Well, it's less than 1.
Yeah.
Is that first limit, is that an h or an n?
N.
When it's between -1 and 1.
Wait, yeah, when it's the decimal.
Not to say decimal, what about 1.5?
-1 and 1.
1.5 raised to the infinity or raised to the n as n goes to infinity? So, the only time this will converge,
That just makes it, just puts it on the
Between
ball.
-1 and 1.
That's just plug it in.
Okay.
when R is between -1 and 1.
That's right though.
Cannot be equal to 1, cannot be equal to -1. But when R is in between -1 and 1, why? Because when you multiply by some number that is in between -1 and 1, isn't it decreasing the quantity? True? Okay. So, and hold on, pause. Just because it decreases the quantity does not mean that any series where the terms are decreasing is going to converge. That is not true. Not true, not true at all. However, we can say for a geometric series, if r is in between -1 and 1, raising it to higher and higher powers will lessen this, and this is the term or part of the only part of this function that has an n in it that even depends on the variable n. So if this approaches 0, therefore this entire constant will converge. And it'll converge to, well, if that approaches 0, then I just have a sub 1 all over 1 minus r. And that comes back to the beginning. Geometric series. If we have a geometric series, it will always converge if r is in between -1 and 1. It will diverge if r is anything greater than or equal to 1 or anything less than or equal to -1. And if it does converge, it will always converge to a sub 1 over 1 minus r. There's a lot contained in this. Ooh, endeavor card. Endeavor. Number.
13? 14?
I want to think 13.
13, let's go with Corey and hope he's right.
I say 12.
I think it's 1 and 12.
I think it's 13.
Am I right? Whoever did it, I'm gonna get small, sucker.
We'll double check. Okay. So, ready, set? For sure. Ready, set? Pause, write down, and as you write down, I want you to identify who is R. Pause, write down number 1, and as you write down, identify what is R. And as you identify what is R, take the endeavor card and make your mind, make the connection, okay, from that R, will this series converge or diverge? And from that, diverge, done, box it, over. Converge, ooh, there's a formula I should plug in to see what it converges to. 1 plus a half plus a fourth plus dot 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 plus, ooh, here's the a sub nth term. Important to know that this is called the nth term. Nth term, we don't know. Sorry, I said I apologize. What do you guys get for R for number 1?
1/2.
Since R equals 1/2, the infinite series n equals 1 to infinity of 1 over 2 to the n minus 1. Wait, does this work? Plug in 1, 1 minus 1 is 0, anything to the 0 is 1. Oh, yeah, it works. Converges, right guys? 2. 1/2 is less than 1.
-1/3. Oh, my bad. I think there's 2 at
2.
The terms approach 0. The sum
Oh,
approaches, look at your endeavor card, there's the formula.
2?
2, 1 over 1 minus
1/2.
a half. Which equals, if you had to simplify, 1 minus a half is a half, and then flip it and you get 2.
Oh, sorry.
Okay? Oh, I understand. Be careful, because that's the most common mistake. It's like it converges to 0. No, the terms do. The series does not. Number 2, you guys should already be writing it. You should already be saying who is R, and from that R, be able to make a conclusion, and from that conclusion, knowing whether or not you should keep going to solve with the formula.
Oh, so R is
3/4.
3?
3/4.
No.
Isn't it?
3 times 2 is 6.
Negative
It doesn't
3.
work. Isn't it?
Oh, it's -1/3. There are
Negative
-1/3. but-
So
Since R equals -1/3, the infinite sum, yes, I'm not kidding about writing it out, n equals 1 to infinity of -1 to the n minus 1 of 1 over 3 to the n minus 1. What's your conclusion?
it converges.
Converges, because -1/3 is in between 1 and -1, right?
1 over
2,
1 over
3.
1 plus 1/3.
Oh, 3/4?
3/4.
then I go ahead and subtract, that'd be 4/3, right? Which would end up,
3/4, yeah. Let's go. So if he doesn't, you can't find R, do you just say diverges?
You have to be able to find R. If R is greater than or equal to 1 or less than or equal to -1, it diverges. If there is no R, this test fails, so hopefully you wouldn't ultimately end up using it. Number 3. Wait a minute, he's not so pretty. Think about him. Plug in.
1/8.
Wasn't there something in one of our homeworks where it said write the first 4 terms, first 5 terms, first whatever terms?
Yeah.
Plug in 1, that's 1/2, right?
1/4.
Plug in 2, 1/4, okay, we get the idea, right? Okay, you guys tell me your full answer.
Since R equals 1/2,
Since R is
the infinite series equals 1 to infinity of 1 over 2 converges to 1 over 1 minus 1/2.
Isn't it 1/2? Because ours is,
2. Let's go.
Wait a minute, didn't we just have one just like this?
That we did, but it was
What was the difference?
the first term.
They gave us the numbers. It was n-1.
Interesting, so they can appear different ways, huh?
Yes.
Pause, you're wrong. They're similar, they both converge, you're wrong here.
It's not the ratio.
0 to negative.
Because 1 to the 4, it wouldn't be 1 over.
Thank you, it's 1/2 over 1 minus 1/2.
I'm sorry.
Oh.
It's a sub 1, that's okay, we have to learn the formula. It's a sub 1 over. This one started at 1/2, it didn't start at 1. Now I can say that's 1/2 and 1/2 divided by 1/2 is,
Let's
Careful.
go.
Oh,
okay, long story short. Geometric series is the first test in section 9.2 that's posted online in your class folder handouts place. The homework assignment online for chapter 9 OT, other textbook, our chapter 10 intro, I think I wrote the whole shebang, is there for the problem numbers for the homework that's on the class folder. If you guys are like, that's annoying, download the PDF to your phone and or computer, you can access it from anywhere, not to worry about Google Drive and all that stuff. Sound good?
Yeah.
All right. And then tomorrow, having found the homework and started it, we have one more test to cover, the divergence test.
This is what we do in our
Yeah. Keep it going. You can call it like chapter 9. OT. Oh, they're right here.
homework's due Thursday, right?
Yeah.
Okay, sweet. I'll grab it tomorrow.
Bye, everybody. Grab your homework.